Alright, so this is our Honors Chemistry lesson video for section 8.1. And so in chapter 7, we focused on ionic bonding and crossing charges and things like that. In chapter 8, we're going to focus on covalent bonding. And obviously it's time to leave school. I didn't realize we were having bells today. Alright, so when something is formed by covalent bonds, it's referred to as a molecular compound. So a covalent bond is formed between atoms held together by sharing electrons. So in ionic bonding, one atom actually loses electrons, the other atom gains the electrons, and then because they become positive and negative, they're attracted. Well, in a covalent bonding situation, both atoms need more electrons. So since they can't both gain the electrons, they end up sharing the electrons. A molecule is just a group of atoms joined by covalent bonds. And then a diatomic molecule is specifically two atoms bonded together. Now, it can be two of the same atoms. Like, for example, it could be H2, it could be O2, or it could be two different atoms. Like, it could be HBr or NO, like that. But as long as there's only two, that's what makes it diatomic, because, of course, di means two. So, there are 7 naturally existing diatomic elements. And they are easy to find on the periodic table because you start at element number 7, which is nitrogen, and you make a big 7. See how this looks like a 7? So it's NOFClBri, but that's only 6 elements. You just have to remember hydrogen. And so what it means is when these elements are by themselves, they are always diatomic and have a 2. So like the oxygen you breathe is not just O, it's O2. Now, once they bond with something, they don't have to have the 2 anymore. So like, for example, hydrogen is H2, oxygen is O2, but once they bond and make water, it's H2O, and oxygen is no longer diatomic. Because at that point it's bonded, and so it forms in whatever ratio is needed to make them all stable. So the 2 happens only when these elements exist alone. Once they bond with something, you have to figure out what the subscripts are by either crossing charges, or if you're doing a molecular compound, by writing the Lewis dot structure. So, we've talked about properties of ionic compounds in chapter 7, and that was they have high melting points, they're crystalline solids, they're made of a metal and a nonmetal, they're made of ionic bonds, and they're good conductors if they're melted or aqueous. So remember, melted is molten, and aqueous just means dissolved in water. So, molecular compounds are literally just the opposite. So if you know this list, just take everything and make it the opposite, and that's pretty much what we have. So molecular compounds have low melting points. They tend to be gases or liquids. They're only made of nonmetals, they're made of covalent bonds, and they tend to be poor conductors. So if you're just looking at a formula only, like NaCl or H2O, the best way to tell if something's ionic or molecular is this part right here. Molecular compounds are usually made of only nonmetals, and ionic compounds are usually made of a metal and a nonmetal. So just looking at the formula, that's the best way to tell. So when covalent bonding is dominant, most compounds exist as molecules, have low melting and boiling points, and exhibit non-electrolyte behavior. So non-electrolyte behavior just means it does not break into ions that can move and conduct electricity. When ionic bonding is dominant, most compounds are brittle solids that have a crystal lattice structure, they have high melting points, and exhibit strong electrolyte behavior. So ionic compounds, when you dissolve them in water, they will separate into their ions. Those ions have the ability to move, which allows it to conduct electricity, which is electrolyte behavior. So this is just kind of a repeat of what I just talked about in the previous slide. So a simple approach to decide whether a bond is ionic or covalent is to assume that a bond between a metal and a nonmetal is ionic, and a bond between two nonmetals is covalent. The problem with this approach is that there are many exceptions. Okay, so this is kind of just like a rule of thumb. Like if I needed a quick way to kind of decide, I could use this approach. We'll talk about many throughout the year. So for example, Sn and Cl, Sn is a metal and Cl is a nonmetal, but yet it tends to have covalent bonding. So what can we do in that situation? Well, another approach to tell if a bond is ionic or covalent is to compare the electronegativity difference between the two bonded atoms. And I'll show you how to do this in section 8.4. So an electronegativity chart just shows us the atom's ability to attract electrons. And so when you subtract, if the difference is greater than 2, we consider the bond ionic. If it's between 0.5 and 2, we consider it polar, which we'll talk about what that is in section 8.4. And if it's less than 0.5, it's considered nonpolar, which again we'll talk about in section 8.4. So for now, what you need to know is if the difference is greater than 2, we consider it ionic. If it's less than 2, we consider it covalent. That's what you would need to know for right now. Now again, the problem with this method is that there is no difference in the electronegativity values for the transition metals that can have multiple charges. So see, lots of these systems that we come up with in science is us trying to figure out how science is working. But science is going to do whatever it wants to do, and so we always have exceptions to the rules. So the rule of thumb for transition metals and those type of compounds is that the higher the charge, and usually that means a +4 or higher on a transition metal, the more covalent the bond. So if you look back on the previous slide, SnCl4, Cl is -1, but there's 4 of them, so that's -4. So tin has to have a +4 charge. So that's why, even though this is a metal and a non-metal, that's why it tends to be more covalent. And so, like I said up here, if you look at an electronegativity chart, tin is only given one electronegativity, whether it has a +2 or a +4 charge. So that's why sometimes that method doesn't work as well. A molecular formula is the chemical formula of a molecular compound. It shows how many atoms of each element a molecule contains. So H2O tells me there's 2 hydrogens and 1 oxygen. A molecular formula shows the actual number of atoms, while a formula unit shows the lowest whole number ratio of ions. So a molecular formula, like for water, H2O, tells me in a water molecule there are literally 2 hydrogens and 1 oxygen bonded together. Whereas a formula unit for an ionic compound such as NaCl, sodium chloride, this just tells me the ratio. For every 1 sodium ions, I have to have 1 chloride ion. It doesn't tell me exactly how many, it's just a ratio. So, our first section assessment. Now I know you're probably thinking, boy, this chapter is starting out pretty good. This is literally one of the longest chapters of the entire year. There's going to be so many lesson videos for the other sections, I don't even want to begin to think about how many it's going to be. So enjoy this short video while you have it. So number 1, how are the melting points and boiling points of molecular compounds different from ionic compounds? Well, molecular compounds tend to have lower melting points and boiling points. So the melting points and boiling points of molecular compounds are usually lower than ionic. Number 2, what information does a molecular formula provide? Well, remember, a molecular formula is just like H2O. It tells the number and types of atoms in a molecule. Where a formula unit tells us the ratio of ions. Number 3, what are the only elements that exist in nature as uncombined atoms? Well, those would be the noble gases. And then what term is used to describe such elements? The term is inert. Sometimes people even call them the inert gases instead of the noble gases. And so remember, they exist as uncombined atoms because they already have full valence electron shells. So they don't have any reason to lose or gain or share electrons. They're stable. So they don't form compounds very often. All the other elements, they either need to lose some electrons, they need to gain some electrons, they want to share electrons, so they are constantly forming compounds, whereas the noble gases are not. Number 4, describe how the molecule whose formula is NO is different from the molecule whose formula is N2O. Why this is a question, I don't even know. We can clearly tell this one has 1 nitrogen and this one has 2. Okay, so N2O has 2 nitrogen atoms. And of course, NO just has 1 nitrogen atom. It's kind of a no-brainer question right there. Alright, so let's move on because I think there's one more section assessment question. Yep. So it says, give an example of the diatomic molecule found in Earth's atmosphere. Well, remember, our 7 diatomics are N, O, F, Cl, Br, I, and H. And so the most common one that students usually give me, of course, is oxygen, O2. However, most of our, the composition of our air is actually nitrogen, which is N2. So you easily could have said that one also. All right, so like I said, enjoy the length and the level of difficulty of this video because the rest of the sections, it's about to get real.